wasn't sure about the shot, so I was waiting for you.
Depends where he wants.
Yeah, exactly. Allow. Pull it in your face.
There's no microphone.
Hi,
Hi, how are you?
Is the conference working?
Yes,
Great.
except
Allow it. Allow it.
I did.
No.
Okay, let's do this. Yeah, okay. Maybe we put it over here.
I wasn't sure if he was gonna stand there and say something.
Speakers. Where are the speakers?
Check the output on the system preferences.
Right.
Yeah. Sound. And then output. Headphone port. Yeah, should be good. The sound get pulled off.
Okay.
Sorry, it was turned off.
Okay.
I don't know how it got turned off. No one should have their hands in here. Even me.
Yeah, that's good.
Or like there. There? Or the class. These are your classmates. Say hello.
Hello? Yeah, I can hear.
Okay, we're good.
Awesome.
Thanks.
I was introducing you to your class.
All right.
So hi everyone, this is CVN student. Yes. So is that where you're gonna sit? You want me to?
No, just sit here. Just sit over there.
I'll point it that way.
Sure. So this is going to be 10 minutes, and then we take this off.
Right.
That's fine.
Right.
Oh, hi, we can see you now.
Nice.
Awesome.
Yeah, so the first presentation is by Steven and students, then we will switch to English students.
Okay,
You
Dan.
can get it started now. Thank you.
Okay, is everybody ready? Is it ready?
Yeah. There you go.
All right. Okay, my name is Don Jones, and I'm a CVN student. A little background on me. I spent some time in the Navy working on electrical distribution systems, and now I'm working at a data center doing power monitoring and control. And my research proposal for power systems analysis is some various methods of braking to improve transient stability of power systems. So specifically, the two methods that I want to study are thyristor controlled braking resistors and an induction brake. So there's some pretty like math-heavy ways to study this Lupin's method and numerical integration to find solutions to the swing equation. This is pretty similar to the homework that we did last week. For the purpose of the presentation, I'm going to use the equal area criterion for stability because it gives a pretty intuitive look at the concept I'm going to study. All right, so equal area criterion for stability. We superimpose electrical power and mechanical power. And we have an equilibrium where delta, the phase angle, is where electrical power and mechanical power are equal to each other. All right, so during a fault, what's going to happen is that you're going to shed a bunch of load and your electrical power is going to reduce to way below what your mechanical power is. So your rotor is going to begin to accelerate. The area between mechanical power and electrical power for this time period is the area of acceleration where your rotor, the value of acceleration is equal to the area between those two curves. So after the fault is cleared and we start bringing the load back on, shutting circuit breakers, your electrical power is going to increase to above mechanical power and you're going to begin to get deceleration in your rotor. This area is equal to the amount of deceleration, and stability is ensured when the area of acceleration is less than the area of deceleration. So the focus of the research that I'm going to do in the next month is manipulating certain parameters to ensure that the area of acceleration is less than the area of deceleration. So again, the two methods that I'm going to consider are thyristor-controlled braking resistors and induction braking. So the first one, thyristor-controlled braking resistor, you would put a resistor in parallel with the infinite bus downstream of your generator, and you would control the amount of power that's shunted with a thyristor. So again, you have equilibrium when electrical power and mechanical power are equal. And during the fault, your electrical power goes down significantly below mechanical power. But if you put a resistor in there, you're able to absorb some of that so that the total area of acceleration is less than what it would have been without the resistor there. The effect being an improvement in transient stability. The next one, induction braking. It's basically like regenerative braking on a car or anything. It's just an electric motor basically that will produce a counter electromotive force when you apply power to it. So this one, it will decrease the mechanical power in order to decrease that area of acceleration. So producing the same effect that you have increased stability in your system. So that's just kind of a short summary of the research that I'm going to do. I used equal area criterion because it's pretty intuitive to look at and understand, and the research is going to focus on Lupin's second method and numerical integration to actually solve these problems. You can direct any questions to my email, it's listed right there.
Okay, thank you. Thanks, John. So we're going to put you off the screen and we go move on to the second presentation. You want to do the second? So let's, yeah, let's follow this. Oh, we need to. You also and put this in your pocket and just hang this. I might have one in my bag. So what Mac is that?
No, it's a Dell.
Dell, okay.
HDMI.
quite dim.
Probably should go to CV and ask them how to switch. Let me go to CV and check.
Okay.
So if you put your presentation on flash memory, it will be easier because you can use this desktop computer.
So, anyone has a flash driver? No. Thanks. Oh.
I thought 3 should be. Is this the right connector?
Yes.
Might be the last one.
Let me just get the key.
Sure. Is there anyone whose presentation is ready at a flash memory? Yeah. Can you do it now? No. Do you want to give your presentation now? Are you giving a presentation?
Yeah,
Can you do it now?
yeah.
Yeah, let's put a flash memory, not on your laptop. Yeah. Okay, great. Now you want to make sure that the piece one is working. Before you use the gesture. There are 13 presentations, so it takes less than 2.5 hours. You have it? Okay, she's coming.
不是他说要自己带电脑。
对，他说 set up。
Actually, try to use that one. The laptop didn't work. So let's try here. If it's working, we okay, give us a second. Here, but this one is not working, right? That's it. Right. So let's try here. Okay, great. Thank you. Let's take you a bit more. Thank you for the presentation.
Oh.
They don't need to point it.
Oh.
Yes, that one.
That's for you?
Yeah, his name is David.
Great, yeah. Use this.
Yeah.
Just put this in your pocket, yes, probably. Thank you, sure. It's already on. Now, when you give a presentation, it's good to introduce yourself, if you're a master's student, PhD student, what department. So give some background information.
Does this work actually?
No, you cannot use that.
To switch
You really
between.
probably should use a keyboard.
Okay, all
It's
right.
not the most efficient one, but
Yeah, it's fine. It's no problem. Okay, hi everyone. My name is Shan. I'm PhD student in electrical engineering department, and I will present my course project. So I want to talk about dynamic filtering for system state estimation. I will give some introduction, talk about Kalman filter, and I want to talk about two different approaches of how we can solve this problem. So as you know, the smart grid will be the power system architecture for 21st century. It incorporates some novel modeling, such as the joint modeling of transmission and distribution networks and the incorporation of renewable energy resources. For this reason, the accurate and scalable state estimation is important more than ever for the reliable operation of this power grid. And dynamic filtering has the advantage of using the temporal dynamics. So usually the Kalman filter, the linear Gaussian, or the standard version of Kalman filter is defined as you have the power system state, and then this follows a linear trend, and also your observation is a linear function. In this case, the Kalman filter, the optimal Kalman filter has two steps. It predicts the system state at first before seeing the observation at time k, and then it updates it. So for power system, we have a quasi-steady state model where we have a linear state transition, but the measurement function is nonlinear. So in this case, we cannot directly apply the linear Kalman filter. Instead, we use the extended Kalman filtering approach where we derive a Jacobian matrix h of k from the nonlinear function. And after doing this, the Kalman filter updates could be applied. But the problem is this is a first order approximation and it usually has poor performance. And a better and also computationally cheaper approach is to use point-based filterings. In this case, as you can see, we have actually the same updates as the Kalman filter equations, except that we have these three variables which contain the nonlinear measurement function. In this case, these nonlinear measurement functions could be approximated by using deterministic points, also called as sigma points. And the unscanted Kalman filter and also like the Kubicher Kalman filter and central difference Kalman filter, they are all based on this. And they usually have better performance than EKF. And as you can see here, we have a simulation obtained by the MatPower toolbox. And as we can see, the point-based filters significantly outperform the extended Kalman filter. And then my idea is if we could somewhat extend this, like if we can somewhat obtain a better dynamic estimator. So the first approach I considered so far was this variational inference on state space, where your state space distribution follows a stochastic integration. So the problem with this approach is, we approximate the prior using the endpoint of this integral, because this integral is difficult to evaluate. And the rows of this matrix follow a Brownian motion. And then we could write the posterior using the Bayes rule. And due to the variational inference, the optimal Q distribution is given by this expectation. And this is the joint distribution. For this, we could derive the variational inference updates. And these become the new Kalman filter. So this is the prediction step, and these update equations become the update step. Unfortunately, this approach hasn't worked so far. As you can see, this new approach actually has produced even worse results than the extended Kalman. Unfortunately, these are my results so far. So the second approach that I still want to consider relies on the tree-weighted sum product algorithm. Here, each bus is treated as a random variable. So power flows are defined between these buses. So it's like the buses are vertices and the branches are edges, and this gives rise to a structure called a Markov random field, which corresponds to an undirected graphical model. So exact inference requires a junction tree algorithm, but the problem is its complexity is exponential in tree width, and instead the problem can be approximated. So there are approximations such as the beta approximation or the loopy belief propagation. And then the problem is this approximation yields a non-convex optimization problem, but a convex relaxation is possible if we upper bound the log partition function of exponential family, which yields a three-weighted sum product algorithm due to Martin Wainwright. And as you can see, this becomes the message passing update equation for one iteration. And this is actually taken from a paper by Wang. And it actually shows that it could outperform the static estimation performance of Newton. So I think so far my problem is that the variation inference I derived on state space cannot handle, because actually that method works fine in lower dimensions, such as the sensor tracking problem. But for higher dimensions, such as the power system, it just fails. So I guess we just need a refinement such that we could run a variation inference in state space and node basis, and it seems to be promising. So the next thing will be to implement this and see if this works with the dynamic model.
Sounds great.
Yeah. So, yeah, this is.
Okay, thank you.
Thanks.
So who's next? You wanna? So what was your name? Pedro.
I will just leave the USB.
No, you can. You have your or flash memory.
Yeah.
Okay. Thank you.
Yeah.
I just need the microphone.
Oh, okay. Yeah. Yeah. Sure.
If you can, for those of you who came late, if you can put your slides in a flash memory, that would be easier. Because see that there is a problem with we're switching between this desktop and your laptop. We can try it, but it's better to use the desktop first.
All right. I'm Pedro. I'm a master's in electrical engineering here at Columbia, and my research will be on the solar opportunities for the Brazilian market specifically. So kind of what I'm going through over here is talking about a little bit about the Brazilian structure, because it's a little different than the US, different how their commercialization is done, our distribution for their generation, and doing kind of a historic analysis and projections so I can talk about the solar opportunities. All right, this is the structure for the Brazilian market. This is kind of like all politics. Sorry. All right, this is kind of a politics, and that's like the operation, like NL, CCE, and ONS. All right, ONS is actually the operation part. The NL is like the regulation, and the CCE is where the commercialization is done. All right, talking about the commercialization. In Brazil, we have actually two different types of market. You have like the captive market and the free market. The captive market is where the generator deals with the distributor and the consumer gets it directly from the distribution. And that's for like less than 3 megawatts loads. So that's like mainly all of us and small companies, all right? For the free market is either like companies or industries that are over 3 megawatts loads, and you can talk like directly to the generator, distributor, and also CCE. So that's like an opportunity for like paying less for the electricity than you would pay on the captive market. So this is the Brazilian generation distribution. We are mostly hydroelectrics. We have 70% of hydroelectrics, and for solar we only have 0.005. All right, so we have like I'm gonna show later the opportunity that we have to implement solar into hydroelectric. So this is kind of an analysis, historic analysis of the reservoir levels for the north and northeast region. I'm gonna show later for the rest of the country, and as you can see, since 2009, the reservoir levels have been going down, and that's a critical thing because we have to turn on emergency thermoelectrics to generate the power that once came from hydroelectrics, and we also need something to raise up this reservoir levels. Same thing for the south and southeast region. All right. So on here on the left side is a Brazilian Institute for Climate Change prediction for the 2040 precipitation in Brazil. And as you can see, matching up with the hydroelectric's location in Brazil, as you can see, this whole southeast region is going to get less than 5,000 millimeters. So that's kind of also an alarm over there for the Brazilian part. And doing an analysis on the hydroelectrics, where we have the most hydroelectric power being generated, and the solar irradiation. As you can see, the northeast has the best solar irradiation, but still on the southeast region, you have like great solar irradiation as well. That's around 1900. So making kind of a little comparison with like Germany, that they have like 5% of generation from solar power. As you can see, the Brazilian's potential is like almost 2 times more than Germany. This scale is a little different over here, but as you can really see, but it's like the average in Germany is from 900 to 1200, all right? And Brazil is 1500 to 2400 kilowatts hour per. So we have solar opportunities for Brazil, not only for the residential, as we saw the GHI indication there, but you have all these reservoirs areas that you can use to generate solar power as well. You have like these floating panels on the reservoirs that you can generate power, and that can be used by the Brazilian companies in like 2 situations. That's why I talked first about the captive and free market. You can, like, if you're not meeting the demand that you sold for, let's say you sold for 20 megawatts and you can only produce 18 megawatts because your reservoir levels are low. So you can use the solar generation to meet that demand, so you don't have like to go on free market and spend more money to buy on the free market and make your agreement. Or you can also use the extra generation that you have to sell it on the free market and get some more money. So my analysis will be on that, focusing on how economical viable is this and how can this be used. So the conclusion is that Brazil still has great room and potential for solar expansion. It can be used both for residential and for commercial use, like I talked here. It has a great fit in the Brazilian commercialization for the companies. But we still have lots of challenges. That's like we don't have like we saw, we don't have like that many solar panels being produced. So the chain of production is still like really pricey, and we still have to work on that. All right.
Okay, thank you.
Thank you.
Who would be next? Who wants to be next? Slides on flash memory. Maybe I should call names. Jonathan? You will talk now? Sure. Yeah.
Oh, yeah, flash, right? Okay, good. Sorry. Good.
The next person would be, go by the way, Chang Hu. You got it here.
attach this.
Yeah, that's really good.
Okay, so for my name's Jonathan. I'm an undergrad EE student. For my project, I wanted to talk about renewable power sources and really get into the progression and future of renewable energy. So before I do that, I'm just going to go quickly through solar, hydro, and wind energy. So solar energy, we all know it's dependent on sunlight. So sunlight has photons. Photons essentially go through a reflective layer and allow us to produce free electrons in material. And the free electrons, when they start to move around in the material, they create a current which creates electricity. So the Shockley limit dictates that we get around 33.7% efficiency, assuming we have a single PN junction. Solar trackers are devices able to orientate a photovoltaic panel towards the sunlight. So we can use algorithms and systems to actually increase efficiency of our solar panels using these type of systems. Then, of course, we have wind energy, which we spoke about in class. We have the equations we talked about in class. We have a general diagram describing the system where we basically have wind that has a force against blades and turns. As it turns the blades, we use induction to create power, and we use a feedback system to essentially protect the system from any damage. So Ben's law, which was published in 1919 by a physicist, assumed that the maximum power that we can extract from wind via a wind turbine is no greater than 16/27, or around 60% of the kinetic energy of wind. Today, we reach around like 40% efficiency of wind power. So this is just a quick video to just. Okay. So I can't play it because I didn't realize. I forgot to drag over the video. Basically, it's a video where it's showing you how incredible a disaster can be for a windmill. Windmills, when they explode, they can explode up to half a mile or a mile long. You can see debris up to a mile long, possibly, when these things actually explode. So yeah, this is definitely a safety concern. Hydro energy, kind of similar to wind energy with respect to turning a turbine and using induction to generate electricity. So we can use solar and wind energy to actually increase our reservoirs by pumping water upwards, and we can reuse that kinetic energy. We can use the potential energy as kinetic energy in the future, as we previously spoke in one of our lectures. So main disadvantages of renewable energy, there's health concerns. In Denmark, there was something called wind turbine syndrome, where they placed turbines too close to civilians, and the decibel of noise was too loud, and it actually made them lose sleep and made them a little bit sick. Safety concerns, windmills can be very dangerous when a disaster occurs. Cost efficiency, wind turbines can cost around $50,000 to $80,000 for a 10 kilowatt machine, which essentially powers a home. So one of these things breaks down or explodes, you're losing 50 grand or more. Solar panels, it's around $50,000 for 6.25 kilowatt system. There's also issues with changing infrastructure, and of course, there's situations where you can damage the ecosystem, such as in California. There are birds that fly around wind turbines because of animals and insects that are attracted by animals, and the birds that come near those areas are actually being killed. It's a big enough issue to the point where the government had to show reports of the birds that they're finding dead. So that's something you want to keep in mind when you're designing a location to install wind turbines. Advantages, when it's used correctly, you can actually improve the ecosystem. There's long run stability when integrating it with power grids. So once you update the power grid, it's a sustainable source. You have it for as many years as the system lasts. new research and insight into effective implementation can lead to a lower cost of living for everyone around the world. So it's a booming business. Previously spoke in one of our lectures. Wind energy in Denmark is actually consists of around 39% of the energy that Denmark actually use. In California, it's around 6.57% of the state's gross system power. Google uses wind turbines to actually power its servers, and they're even looking into further research in terms of a flying kite. So essentially, instead of using a big infrastructure from wind turbines, you're using a kite that can generate electricity. Once it's up in the air high enough, it can actually last for a long time and actually generate electricity without having a large infrastructure. You're reducing the weight of the blades that you're actually using to generate induction. So it's a live market. This was bought in 2003 by Google. So recently, oil prices have been dropping, and that's not a problem. There was an article basically making the point that you're comparing apples and oranges when you compare fossil fuels to renewable power sources. Fossil fuels we're ideally still using for our vehicles because of the infrastructure and how it's built. It's easier for us to use oil to power our cars, but there's still that appeal of renewable power systems in terms of our home. Our homes are disconnected, are connected to a power grid, and they're able to obtain energy easily from the system, as were cars. Electric charging systems still haven't really grown that much. And just recently, Tesla has been making a move on the economy in terms of pushing for electric vehicles to become a part of our lives. So playing the energy game, it's all about just searching for the ideal location to implement solar, wind, and hydro energy in terms of taking advantage of all the advantages of this system. So business opportunities only continue to grow as we understand wind, solar, and hydro energy more. So it reminds me of a game of like Catan, where you basically settle down and take advantage of materials on the playing board, and then eventually, when you build a large enough system, you essentially own the game board. So it's all about finding ideal locations to maximize your energy profit. So in searching for ideal locations, there are a lot of places in the Caribbean that actually have ideal wind flow models. So Dominican Republic, at the moment, there's only 3 wind farms, and they're around the areas where there are hotels. And it's interesting to see how some locations are able to generate more kilowatt with less turbines. So again, finding ideal locations early is the ideal way to implement the future of renewable power sources. So the future of renewable energy in the U.S., as you can see, so wind power has basically taken a large rise from around like 80 years ago. So as you can see, like it's been on a constant increase, and in general, all renewable power sources seem to be increasing steadily. And these are my sources.
Thank you. The next person would be Alex. Alex, here. Do you have a flash drive, or you want to use your laptop?
I don't have a flash drive.
Okay, let's try your laptop.
Or if I can get access to the...
Let's try it.
Or doesn't have to use like a Dropbox or something.
It's better to do slides. That would be much better.
It takes time. Okay. And use the microphone. Sorry. So you can use your laptop.
Okay. So my name is Chang, and I'm a master student in electrical engineering major. And today's topic is about DC boost converter applied in solar power systems. And here's in this presentation, I'm going to give a brief introduction about what the solar panel is and something about its electrical characteristics. And then it will talk about what is a DC boost converter and why we need it. The last part is some simulation due to my recent project. And the solar panel is a device that can converting the solar energy into electrical current directly. And the material is the typical material is like the semiconductor devices like gallium arsenide or polysilicons. And the radiation from the sun will hit the solar cell with like two layers, named the P layer and the N layers. And the boundary between them will act as a diode, like allowing electrons to move from N to P. And when the photons with sufficient energy hit the cell, they will cause electrons to move, and thus will generate current. But notice only the sunlight with a certain energy will work efficiently, which means most of the sunlight will be either reflected or absorbed. And a typical commercial solar cell has only an efficiency of about 15%. And the power, the output power will highly depends on multiple factors like the operating temperature and the solar radiation, number of the cells, like whether they connected in series or in parallel. And in this figure, we could see like how the temperature affects the output current. Since your output power will equals to your voltage multiplied by your current, it will show that a curve like that. And this part is the power array instead of the single power cell. It's made by multiple power cells. And the operation voltage will be multiplied due to the number of the array. And from the previous figure, we could tell that the best operating point due to the operation voltage will be different due to your factors. So in order to maintain the PV system operating at the best output power, operating power, we need a device like a DC boost converter. It's a simple switching voltage converter, like the output power. The output voltage will be controlled by the on and off of this MOSFET switch. And it generally have 3 different operating phases, like the T stays on, D stays off. Left part is called like a T state. And at this part, when the MOSFET switch is on, and the current will flow at this part, and the inductor will store energy. And when the switch is off, the sudden change of the current in the inductor will cause a backward electromagnetic field, which works as an extra voltage source, so that the capacitor can be charged with the voltage higher than the applied voltage. And in this phase, the capacitor will provide the power to your resistive load. But notice at the last phase, since your power is supplied by a capacitor, the voltage will keep decreasing, so it cannot last long, which means we have to recharge the capacitor rapidly. But this circuit also has some disadvantages. Like in the first stage, the MOSFET will have the resistive of the first stage will be quite low, which will work at a short circuit. So the current flow into, from the inductor will be fairly large. We cannot keep the first phase operating too long time. And also, if we don't have the resistive load, when it operates as the third stage, the inductor will generate a fairly high value voltage, which may be as high as hundreds voltage maybe. And that will burn the diode. And here is the simulation figure from my recent project. And the first part is the mathematical model for a PV cell, so that it can take the applied voltage, solar irradiation, and the temperature, and calculate your output current and work as a current source. Then by connecting it to this DC boost converters, we can control the output power to help it maintain at a constant value. And here, at this moment, I applied a sudden change of the temperature, which caused a decreasing of the output voltage. But the system fast detected that and increased the the on and off frequency of this switch, and to make the voltage, increase the voltage back to the the designed values. So here's the reference.
Okay, thank you. After Alex, it would be Jeremy Patcher. Any of them fits.
Oh, I think I don't need an adapter. Actually, that's so.
You need it probably. Not this? No, it's a little smaller. Yeah. This is the HDMI, but doesn't work for all apples. No, this is smaller than digital. It's a little weird. It's standard size.
Is it upside down?
Oh, okay, good.
Yes. I can just use the flash drive.
Yeah. We tried one last time. It didn't work. No. Probably it's put it better. So, yeah. Yeah. You want the help? Yeah, it should be great if you can try it. I probably should mirror this, but I don't know how.
Right, yes.
Doesn't look like my computer. So. Probably.
We're gonna let this search. Okay, now go to displays.
It's working out.
And then arrangement. And then mirror displays. There you go. Good. Cool.
Thank you.
No problem.
Hi, my name's Alex, undergraduate electrical engineer, and I'm going to be talking about renewable energy grid integration and how it pertains to energy storage. So the main goal is to find solutions to the problems caused by grid integration from renewable energy generators, and like I said, particularly in energy storage. First, I'm going to talk about variability in renewable energy systems, a metric to sort of quantify this called ramp rate, how that pertains to renewable energy storage, and finally, try to solve or reduce the amount of energy storage needed by matching the generation profile of renewable energy generators to the load profile of energy demand. And two things that I've come up with is using a more, for fixed panel orientations, using Western orientations rather than just a traditional Southern one, because I'll show why later, and then hybrid PV and wind integrated energy system. First, we talked about this in class, but what is variability? It refers to the changing of energy production from renewable energy sources due to the availability of those energy sources. So here's a little graphic of variability for solar energy. So during the summer months, you're going to have more production around like noontime during the day. You're going to have the most production, and on the order of minutes, clouds can cause variability in energy production. And for wind, it has very similar structures. The curve's a little different during the day. It peaks during the nighttime instead of like at noon. And on the order of minutes, there can be variability caused by wind speed instead of
Can you use the microphone?
clouds. So ramp rate is a way to quantify this variability. So you can use it to, that's what I'm going to use to characterize and compare like different panel orientations. Basically this equation here is just, you sample the power at different intervals of time. You take two adjacent time points, measure the difference in the power. This is just to normalize it to the capacity of whatever plant you're using, so it would be the capacity of the solar panels, and that gives you the ramp rate. You can use, this term here is daily aggregate ramp rate, and you can have like a given ramp value which you don't want to exceed based on your generator and your grid. Can't really see these too well, but these are just examples of what like ramp rate graphs will look like. So you can see that due to the variability here, you get this big oscillation, and that's bad for the grid. So why is energy storage important? It can be used to counter this renewable energy variability and the ramping effects. So when the energy production goes below the demand, you need to take from the energy storage, and when it's above the demand, you need energy storage to store this extra energy. But why it's most worth exploring is because it's the most costly point of energy integration, and any way to reduce this greatly just reduces the cost of renewable energy integration. So one solution I have is using a Western orientation instead of the traditional Southern orientation. So this shows the production curve from a solar home with Southern panels, and you can see that the peak demand's around noon, whereas here's an energy demand curve, and you can see that the peak demand's around like 5 o'clock. So to better align the peaks, I was thinking using a Western orientation. As you can see here, like a Western panel orientation has the peak time around 3 o'clock, as opposed to the Southern one up here, which is around noon. So the reason people use Southern oriented panels is because it has a greater production. So I'm going to use a model to simulate like different capacities facing west and south combinations to see where I can find a nice balance of still getting a good production but having it later in the day to match the demand curve. And another solution that I have is integrating, sort of having a hybrid system of photovoltaics and wind. Here's another graphic. This is taken during the summer of the New York state load, and this is just the example of wind generation of capacity of 30 gigawatts, and this is sort of what I was talking about before, that it peaks more during the nighttime than during the day. In the next slide, you see generation curve for photovoltaics, which, as I said before, peaks during the day. So I was thinking that if you combine the two, you're going to get a curve that's sort of flatter and that better matches the curve for the demand. And there's a lot of papers out on this, so I was just thinking of like sort of...
Is it realistic curves or just cartoons, these curves? Based on real data?
Yeah, it's based on like July of 2006 for New York. Cartoon. So yeah, anyway, so there's a lot of papers out on this, so I was just thinking about, for this part of the paper, just sort of surveying them and seeing what they have to say about capacity and the best way to integrate it. And yeah, that's it.
Thank you. So, then we Yankee Wu. Great.
What is the interface for switching this? Different slides?
Just here.
That's what I'm saying, and then between slides there's a... Is there a remote?
No, it has to use the arrows.
Okay.
Okay, thank you. Let's see if it's working. Switch.
Okay. Is this let me
Yeah, it's working.
Okay.
And it should be here.
Great. Is it? Let's take a look. There you go. Okay, how do you fix this? Okay. Hello guys, I'm Jeremy. I went home about 2 months ago, and I was home for about 5 days. And within those 5 days, I got 2 knocks on my door that were saying, "Do you want to switch to solar power?" And I thought about it, and I thought, you know, I don't know. And I think what I wanted to do for this project was kind of derive from basic physical principles, try to understand really what are the parameters that are at play here, affecting, you know, whether or not I want to switch to solar power. What are the different, what does efficiency depend on, and maybe in the future, if I do this now, will there be better solar panels in the future that are more worthwhile to hold out? So I'll walk you through basic physical principles without too much pain, just so we kind of get an idea of what assumptions we need to come up with what game we're kind of trying to play when trying to come up with the best solar cell. So, I mean, basically we have a semiconductor device. It's a p-n junction. We take an n-doped and a p-doped. Basically, we have these impurities we introduce, and we have, when we bring these two sides together, we have different physical principles kind of at play. We have basically n-doped, we have excess electrons, and we have these diffusion effects such that we have electrons going from one side of the junction to the other and leaving behind positive ion cores here. And then we have a built-in kind of electric field. We have some equilibrium associated with this, such that there's a potential between the two, and there's in equilibrium, I guess these back and forth play between free carriers going from one side to the other kind of settle out. And we're interested in processes called generation and recombination. Basically, when we have an electron that has gained energy, it moves from the n side to the p side across this junction, and that generates an electron in a hole. It's a pair, electron hole pair. And then once the electron hole pair diffuses from one contact to the other, they can recombine and disappear at the contact or along the way. And I guess depending on where this recombination happens, we can get more current or less current. I'll talk about that later. Okay, so we can think about this, we can kind of understand the game we're trying to play. We have, here's a diode in the dark. We basically have the left side is like an electron injecting contact, the right side a hole injecting contact. We can send electron in the conduction band of the n-type semiconductor. If we apply this sort of forward bias, it kind of lowers the potential barrier, and electrons can more easily go from one side of the barrier to the other. You can kind of go across the junction more easily. So if we inject electrons on the p side, we leave behind missing electrons on the n side. And there's this kind of push to have this recombination happen because the system always wants to restore equilibrium. And yeah, so I guess I'll just keep going because I don't want to bore you guys with that. Get more to this. Okay, so there's this process called the photovoltaic effect. Basically, this is the process by which the solar cell actually converts the sunlight into electrical energy. And we have this situation where photons are coming from the sun with various amounts of energy that correspond to different wavelengths of light. And when these photons are coming in, they can either be reflected, absorbed, or pass through. And we would like to absorb as many as we can. So the situation is that if we have energy bigger than the band gap, which is defined as the energy level difference between the valence and the conduction bands, then we can promote an electron from the valence band, a conduction band, and leave behind empty states in the valence, and an electron in the conduction band, which is now a free carrier. And silicon is a very commonly used semiconductor device for this, and it has a band gap of 1.1 eV. So basically, only photons with energies above 1.1 eV can be absorbed. So the question is, are we wasting energy here? Is there some sort of way we can have multiple band gaps to, really take more out of the solar spectrum? And ideally, every photon with energy above the band gap can be absorbed. But we have these limitations based on the finite thickness of the solar cell. So in reality, that's not the case. So let's try to come up with an idea of how we can design this solar cell. So light comes in, and we make the solar cell as thick as possible. We can make it effectively thick to reduce costs. And we have this situation where we can pull this stunt called light trapping, where light comes in, and if it doesn't get absorbed, maybe it reflects off at some angle and it kind of gets trapped, new passes through, so that has opportunities to be absorbed again. And now we want to collect, once we have generated these electron hole pairs, so we want the p-n junction to collect these carriers. So we have a top thin layer and a thicker absorbing layer. And we want to say, okay, minority carriers that want to diffuse through the junction to be collected out the contacts. Some may recombine before they get there, and some may diffuse to the back contact to recombine. So we want to kind of come up with this structure so most diffuse towards the front and are collected. And we want this collection efficiency to be over 90%. And some of the important parameters I'll just define now so that later on they kind of make sense. We have open circuit voltage, short circuit current, and this thing called the fill factor, which I'll talk more about. So we have this short circuit current and open circuit voltage are kind of talking about the maximum current and voltages from a solar cell. And at both of these operating points, the power for the solar cell is 0. So this fill factor is basically the ratio of maximum power from the solar cell to the product of the voltage, open circuit voltage and the short circuit current. And this is like graphically kind of the area of the largest rectangle with which we can fit in, that we can fit in the IV curve. Okay, so anytime an electron-hole pair recombines in the semiconductor, one electron can flow through the external circuit, and anytime a pair is generated, if it's collected, current can flow, and if it recombines, we kind of subtract from that. So we have carrier recombination that lowers the short circuit current and reduces the open circuit voltage. And here's the situation that we're looking at. Sunlight's coming in, we have this p-n junction, and we're saying, all right, we want to absorb as much as we can from the solar spectrum. And then we can kind of generate this current. Here's the diode current. And it's basically, it has to do with the flow recombination and generation. And I don't really want to go too much into these equations, but here's are ways to kind of model the recombination and the generation rates to integrate over the width of the whole device. And okay. So in a perfect world, we can say, all right, well, we're not going to have any losses associated with different resistances, but if we want to be accurate, we want to talk about a little bit about the model we're going to use, which is that we have this kind of shunt resistance and series resistance. And here's the current in the actual diode, and we can kind of get a feel for, maybe we want to reduce losses, so we want shunt resistance to be big. And I guess this is like an intrinsic property to the diode to have a specific current associated with that. And I guess I'll talk a little, I want to kind of get to this model, so I'll just keep going. So we want to understand, okay, what makes a solar cell good? So open circuit voltage is key because it's easy to get a relatively good short circuit current, and the fill factor, it's hard to make that better. We can only kind of worsen that with series resistance. So we want to have general assumptions that any light created in the device is collected, and that solar cell minority carriers don't combine at the back contact. So there's like a high chance that they're collected and can contribute to the open circuit voltage. And all recombination occurs in the base. So we can equate the recombination and the generation rates and come up with an equation that tells us about the light generated current. And just again, I don't want to get too much into these, but there's some laws called law of the junction that kind of tell you what's going on at these confusing points, maybe at the depletion region, like at the outer edges of the depletion region, and basically playing around with some of this stuff, we can come up with the equations for the open circuit voltage and fill factor, and ultimately the efficiency here, which is what we're concerned with. So to make a good solar cell, we need it to be optically thin, and we want light trapping. We want high doping in the base to get high open circuit voltage, which is kind of a trade-off with carrier lifetime. For when does it recombine? Is it going to make it all the way through? We want like a wide band gap, and we want like a perfect back surface reflector, an ideal emitter. And okay, we'll talk a little about efficiency. If we increase the band gap, fewer photons will be absorbed, and the open circuit voltage increases, and efficiency will increase. So this is actually, I guess I'll talk about this. There's a very famous paper, I guess, published in the late 60s by Shockley, Kaiser, and it's basically says, all right, so where do we want, what band gap do we want for our semiconductor? And assuming we have, I guess certain parameters to, open circuit, we have the fill factor is 1, and the short circuit current is equal to the light generated current. We can see that, we had a peak at around 1 EV, which is close to silicon, which is good because silicon's cheap, and we use that. It's 1.1 EV band gap. And so there's some optimum band gap that exists that I just discussed. We can use silicon. And as you keep increasing the band gap, I want to point out the voltage keeps going up, but the photon number that can be absorbed goes down, so the current will drop. So that's why we have this peak here. Okay, So when I first started this, I was hoping to come up with some sort of model for, what can we do to better make solar cells that, have a higher efficiency in the market, that we get more use out of. And I kind of stumbled upon this, which kind of took away me having to make the model, but I guess I would like to talk about it. We can keep kind of stacking more junctions with different band gaps, and we have some fundamental efficiency limit around 87%. And the idea is that, like I said, we have a semiconductor device with a certain band gap that kind of deals with certain energies of photons coming in. We want to really get the most out of the solar spectrum. So if we keep stacking these, we can have a higher efficiency because we're using more of the solar spectrum. And you can't just keep adding them all the way because, infinitely, because at some point you're taking away current from the other devices. And we can kind of define this thing in this paper by Gray. He defines this ultimate, system efficiency kind of parameter. And he says, all right, so here are the things we got to think about. We have some ultimate efficiency, which is basically if everything is operating at the open circuit voltage, if each semiconductor device can kind of operate at open circuit voltage, and we have the highest possible parameter for that. We have this photon efficiency saying, all right, well, we have all these different wavelength photons coming in and with different energies, and we're saying if we can kind of send them to the right devices to be collected, you have a 2 electron volt photon coming in. You don't want a 1.1 EV device to collect it. You want a 1.9 EV device to collect it.
Can you wrap it up in a minute?
What?
Can you wrap it up?
Yeah, this is yeah. And then we have this interconnect parameter saying there's some losses associated with that. And then we have a weighted kind of sum of like how many photons are kind of going to each semiconductor device. Anyway, so and then I guess the last thing I really wanted to say is that, now that we have this idea, how can we apply this to the real world? My next step would be to kind of say, how easy is this multi-junction thing to implement in practice? And I guess on the market there are a lot of single cell junctions, so single band gap junctions. So what can we do? Maybe we can do a little better, and maybe it's good to hold off for a little bit and wait for a more efficient one to come out. So thanks.
Okay, thank you. After this presentation, we take a 5-minute break, then there are 5 more presentations. Then you can get your homework for at 5 back. Do you have a flash memory? Or?
But I need to play a video.
Oh, okay. So do you have the HDMI connector?
Yes.
That's good. Medium may not work if that's sure. It's probably. Is that yours? Just try it. Just open it. It might be yours.
Let me see. Where is it? Oh, can I play with my laptop?
No, you cannot because you need to have HDMI connector. I don't have it for this laptop.
Okay.
That's fine. Well, let's do something. Take a 5-minute break, then we'll be back and see presentation. 5 minutes, figure out.
Yeah, sorry.
That's fine. Let's do this after.
Mas é que você vai encontrar, cara, isso aí, como é que você vende o custo marginal de operação, se entra nessa conta, eu não sei, cara, você tem que vender, não pode ser metodologia, como é, não, mas a metodologia dele, eu acho que é disponível, tem que ser, não faz sentido chegar e falar, mas aqui, que custo do pé? Não faz uma conta assim, não. Se eu gastar na internet agora, quanto custa no futuro? Agora tem uma, sei lá, eu vou até a terceira mais cara até, vamos dizer. Se eu usar agora a térmica, eu vou a terceira que é mais cara até, vai falar um pouco mais, mas tem lá. Só que daqui a 3 meses, eu vou pensar e eu vou gastar a quinta térmica. Eles fazem essa conta para esse negócio, achava ótimo ver se vale a pena gastar minha água agora, tornar numa térmica depois, ou se eu já torno na térmica agora e continuo com a água depois.
And today is my last office hour. So if you have any question about your project, you have just today to talk to me. 3 to 5 p.m. So I'm traveling to a lot of conferences till the deadline for your project is either like May 15th if you're graduating or June 5th if you're not graduating. But maybe I may not be able to respond to all of your emails. So if you have any questions, come to me today between 3 and 5. So how about the slides? You don't have a slide? Just a video?
I have slide, but I don't want to show them.
Okay, it's up to you.
Então, aí vai depender de como é que é feito esse negócio. Por exemplo, se for iniciativa do governo, esse negócio vai ser feito para ele diminuir o custo de térmica. Ele vai mandar instalar, vai fazer coisinhas assim, para fazer leilão reservatório da tal, tá ligado? Ou, se a tua empresa fizer, se a tua empresa fizer, aí ela vai trabalhar com o quê? Aí ela vai trabalhar com a arbitragem, que é isso que eu falei que eu queria fazer. Ah, por esse tal agora, aí eu vendo. Tipo assim, eu vou ter um limite, lógico, 100% da minha. Você consegue manter o quando a energia estiver cara. E por reflexo, tu acaba diminuindo o PLD, mas tipo, eu não sei como é que funciona assim. Mas aí, tipo, aí você está diminuindo indiretamente, digamos, não é uma estratégia do governo, é uma estratégia da empresa, mas é indiretamente. Mas não sei como funciona.
The next presentation after this is by Shahrukh. Shahrukh Khalkhali.
Eu não sei, por exemplo, se porque quem faz o despacho da hidrelétrica é a ANS. É ela que define se quanto eu vou guardar de água. Basicamente, tu não manda muita coisa. Eu não sei se pode chegar a instalar um reservatório aí e ficar água. Eu acho que não sei se.
Okay, let's continue the presentation. Go ahead. And use the microphone.
Eu não sei, cara, essas coisas tudo eu vou. Eu vou fazer agora.
Good morning, ladies and gentlemen. My name is Dan Chi Wu. I'm a junior student for one semester exchange program from China. My major is electrical engineering, and my field is power system and its automation. Today I want to talk about my project. The topic is Survey on Smart Home Technology and Power System. So what is smart home technology? Smart home has always been considered to be the most potential development chain of interior design industrial. But when it comes to the future of smart home technology, there's one thing we can be sure of. Technology is continuing to improve and innovations are being made, which will definitely increase the energy efficiency and decrease the cost of energy use. Recently, home automation, or you can say smart home control, may include three aspects: HVAC, centralized control of lighting, and security locks of gates. So what is HVAC? HVAC may include heating, ventilation, and air conditioning systems. An internet-controlled thermostat allows the homeowner to control the building's heating and air conditioning systems remotely. For lighting, lighting control system can be used to switch lights based on a time circle or arranged to automatically go out when a room is unoccupied. Some electronically controlled lamps can be controlled for brightness or color to provide different light levels for different tasks. And for security, a household security system integrated with a home automation system can provide additional services such as remote surveillance of security cameras over the internet or central locking of all perimeter doors and windows. Well, the use of these three technologies are quite widespread use in both USA and in China, but the latest technology about this field is iPad home control. iPad home control means you can control your home from the palm of your hand. With wireless audio and video and remote access to the file on your PC, you can use your iOS device with iPhone or iPad to conduct your digital life like an orchestra. You can even monitor the security of your home when away or just keep an eye on your baby. Everything can be controlled with the right apps and accessories just with your phone. At the last stage, I will introduce the top 5 simple smart home upgrades with a video.
Now that everyone has a smartphone, the next big wave in tech is the connected home. Getting everything from your doorbell to your toaster connected to the internet, working together to cut down your energy bill, make your breakfast, and watch your cats. I'm Donald Bell, and if this sounds like the life for you, here are my personal recommendations for the top 5 simple home upgrades that will jumpstart your smart home. Starting off at number 5, smart lights. The Philips Hue is really the king of this category. $200 gets you 3 bulbs and a wireless hub with extra bulbs setting you back about $60 each. Not cheap, but these LED bulbs last about 15 years. Plus, they pack more show-off factor than anything else on this list. Just invite your neighbors over, queue up Dark Side of the Moon, and play with your light bulbs for 20 minutes. Heck, in Colorado, this could be a full weekend of fun. At number 4, smart outlets. A lot of options in this space, but Belkin's $50 Wemo switch is arguably the most well-known. You just plug it in, download the app, and within minutes you've got an outlet that you can control and schedule with your phone. For $30 more, you can add a motion sensor that will activate the outlet when you walk in the room, or freak out your pets all day while you're at work. Coming in at number 3, smart smoke detectors. Pretty much talking about the Nest Protect here, unless you're buying a more comprehensive security system. As someone who sets off my smoke detector almost every time I cook, I would gladly fork over the $130 here for a smoke detector that will talk to me a little bit before going to red alert. It's also room aware, so it can politely wake up my sleeping wife to let her know that I burned my grilled cheese downstairs. Staring at light bulbs makes me a little hungry. At number 2, A smart thermostat. Now here I'm not just talking about Nest. They have one of the prettiest ones, but there's some good connected thermostats out there for about half the price. The bottom line is that here's an upgrade that can really translate into a smaller energy bill almost immediately. A thermostat that adapts to you and sends you feedback on your energy use and even tells you when it's time to change the air filter. That's progress. Now before we get to number one, let's take a moment to call out one of the silliest smart home appliances we've seen, the Crock-Pot Smart Slow Cooker. Now don't get me wrong, I rely on my Crock-Pot for cooking dinners that won't set off my smoke alarm, but why does the most basic kitchen appliance ever invented need an app? I suspect we're going to see a ridiculous wave of unnecessarily smart appliances over the next few years until we collectively figure out what really makes sense. A $99 Crock-Pot does not meet that threshold. All right, and finally, my number one pick for a simple smart home upgrade, Smart Lock. We're seeing a bunch of these coming out this year. Goji, August, Lockatron, Kivo. Some will replace your entire lock, some will fit over your existing deadbolt, but all of them promise that they can be installed in under 20 minutes. A great range of prices and features. Some have NFC and will unlock your door with a wave of your phone. Some will notify you when you get a knock at the door. Some will even send you a picture of the person who's been stealing your Amazon packages. If nothing else, as the first thing that people see when they come to your house, it sends a message. A proud geek lives here. So there you go, 5 products you can buy right now to make your home a little smarter and impress your friends. Be sure to check out CNET's appliance reviews for all the latest in home tech. And for more top 5s from me, top5.cnet.com. I'm Donald Bell. Thanks for watching.
So that's all for my presentation. Thanks for listening.
Okay. So half of the credit will go to the teacher. Video. Next, Sharud, and one after that will be Yuvan Chan.
I'm logged into someone else's. Oh. Sorry, I just need to grab my notes. My name is Sharad Kalkali, and I am a EE undergrad. And my final project is about tidal energy. And the picture we see here is of the Bay of Fundy, which is located in Nova Scotia. And what's significant about this photo is the extreme difference in the high and low tidal landscapes. As we can see, you have this person here for scale. Tide goes up almost 14 feet at high tide. So how do we harness all this water moving around? Quickly, I just want to talk a second about the tidal phenomenon. So a tide is the rise and fall of the surface of the ocean due to the gravitational force of the sun and moon on the Earth in conjunction with the centrifugal force produced by the rotation of the Earth about the moon. So as we can see in this diagram in figure A, the moon is drawing water towards it by gravity. At the same time, from the rotation, water is pushed away. And so the land masses on this axis are experiencing high tides. at the same time, the land masses 90 degrees to this system are experiencing low tides. As you can imagine, this same configuration will occur once again once the Earth is on the other side of the moon. And so there are 2 high and low tides per day, with some variation depending on where. Further, the tidal ranges are modulated by the sun to some extent, more the moon, more the effect of the moon, but the sun creates what we call spring tides and neap tides, which are higher tides in the spring and lower tides in the fall seasons. So where is tidal energy available? Well, it's very dependent upon the tidal ranges. And so what this map shows here is where are there areas of high tidal ranges. Not all of these areas are ideal, but as we can see, there are a lot of sites worldwide where there's tidal ranges of over 150, I want to say meters, probably not. In any case, these are the regions where it's available. And so now, what is the mechanism by which we can capture it? One such way is a tidal barrage. This is one that's not yet built, but has been proposed to be built in the UK. It's called the Severn Estuary. And as we can see, it's a dam-like structure. It's very similar in operation as to a dam, except it's refilled and emptied every day. So on the left, we see what's called ebb generation, and on the right, we see what's called flood generation. So the gates are controlled based on the level of the water outside and in the basin. As the flood tide comes in, the water fills the basin up until a point where the ebb tide begins and the water level begins decreasing. The gates are opened once there's sufficient head created, and the energy is generated as the flood goes out. What is really happening here is we're harnessing the potential energy contained in a volume of water, which is given by this equation, which you may be familiar with from physics. Here, E is the potential energy contained in a volume of water. A is the horizontal area of the barrage basin, rho is the density of water, G gravitational acceleration, and height, H is finally the vertical tidal range, which is the difference in the height of the high and low tides. So what is really making this profitable is having a high tidal range, having a large difference. And we do this by using the gates, or just by picking areas such as estuaries, which have a high tidal range. A similar way to capture this energy is with a lagoon, and this is really the same in operation as a tidal barrage, except the entire structure is man-made. So these are for locations where you don't have an estuary per se, but you still have a high tidal range and you want to capture that potential energy there. Yes, okay. And so what are some advantages and concerns of tidal energy? First, an advantage is that tidal energy is highly predictable. The tidal currents are consistent. We know what they will be year after year. This is unlike other renewables like solar or like wind, which are dependent upon cloud cover, which are dependent upon different conditions. Wind is actually stochastic, I think, in nature. So tidal energy is great for that reason. Another reason, it's very powerful. It estimates that we could exceed 120 gigawatts globally if all of it was harnessed in the best way. Some concerns, the environmental impact of a lagoon or especially a barrage is really similar to that of a dam. So that really changes the delicate ecosystems in estuaries and tidal zones, which are usually fertile breeding grounds or feeding grounds. They're also delicate in their salinity levels. So that's why barrages are not so favored. Tidal cycles also may not match use cycles because tidal cycles run on a about 25-hour rotation because of the lunar cycle. Obviously, the tides won't always match the daily use cycles. So this must be addressed, which I will talk about a little bit later. And lastly, the maintenance is and it's less profitable because of the maintenance also, because they're underwater and they're hard to build. They have to withstand like a lot of weight of water behind them, so they're very expensive. Even though there are several barrages, not so much lagoons, but there are several barrages already built around the world. Tidal current turbines are another way of harnessing tidal energy, and as I will discuss, it is what I think a better way to do it. So here in this picture we see several designs of tidal current turbines. This is a horizontal axis turbine. Next we see a hydrofoil turbine, which sort of acts like a fish's tail or like a whale's tail and sort of just flows in the tide like this. That one is a vertical axis turbine, which is great because it can operate no matter which way the tide is coming, whether it's going in or out, it'll rotate the same. And the last is an open center. So while the barrages and the lagoons were used to harness the potential energy in water, these are really here to harness the kinetic energy in the tides. And it doesn't only work in tidal zones, but there have been tests using them in East River or the Gulf currents of Florida, and they're not as environmentally impactful if we get a little bit more into the mechanism by which they work. So tidal current turbines are really similar to a windmill, like we discussed in class, in operation, and they actually operate by the same general equation. P is equal to 1/2 rho AV squared, where A is the swept area of the rotor and V is the velocity of the water. And what's exciting about this is that rho, the density for water, is clearly much greater than that of air. So tidal turbines generally have much smaller areas and you can fit more of them into a smaller area. Of course, this is the total available energy. This is, again, reduced by some power conversion efficiency rate, which looks similar curves to what we see in windmills. So what are the prospects for the future with tidal energy? The construction of barrages have significant environmental impacts. There's a marked reduction in the water body exchange and the permanent flooding of some intertidal zones in the impounded basin area. The predicted negative impact of the eco-environmental aspects of the estuary need further investigation. But as I discussed, these smaller modular tidal turbines do not have the same damming effect as the lagoons or estuaries. Next, regulating the output characteristics will be very important because, as to discuss, the tidal cycles don't match the use cycles, and so there has to be a way of either storing the energy. In lagoons, they actually use the energy in off-peak hours to pump more water behind it to increase the head to get more potential energy. There's also ways to phase different power coming from different areas in a way that will make them profitable. So in this next diagram, we see the output of several, these are tidal current turbines situated in around the coast in the Scottish coastal lines. And while each one varies basically sinusoidally, and there are these are limited. This paper was looking at how we should limit them in order to make the output, the base load output, as consistent as possible. And so even though these are varying roughly sinusoidally, we see that the output has a smaller range and could be used understandably as a base load. So again, methods of regulating output characteristics. And last, it must be profitable. The estuary projects are very expensive, and they've found government subsidies in the UK and some other European countries, but not so much in the US. But I really think that the tidal current turbines are much more profitable and attractive in their modularity and in their invisibility. They can be deployed easily, and yes.
Okay, thank you. There are 4 presentations. After you'll meet with Shang-Li.
Hi, my name is Ewan, and I'll be presenting on using Simulate to model and optimize photovoltaic arrays. So to give a brief overview of a solar power system, so we have the sun, and it gives irradiation to a PV module. And the PV module can produces direct DC power, which can either be sent to a battery storage, or it can go through an inverter to be converted to AC power, which then either goes to residential or commercial loads, or it can be used to be bought by the utility grid. And so basically, if your PV module that's installed in your home is providing more power than providing more power than what you are using, then the extra power can be sent back to the utility grid. And if it's not using as much power, then the utility grid will, just like normal operations, it will send power to you. In any case, you want to optimize the amount of power produced by your PV module. And so I'll go into that. So to analyze the power that's being produced by a PV module, we have to analyze the current and voltage characteristics. So first of all, a solar module is basically a bunch of solar cells connected in series. So the characteristics of one solar cell is similar to one of an entire PV to one of an entire solar module. So if we connect the solar cells in series, then basically we get more voltage. And then if we connect them in parallel, then we get more current. But the overall shape of the IV curve is still the same. And so basically, from this diagram, as we can see that as irradiance increases, so if we get more sunlight, the IV curve increases. But as the temperature increases, the IV curve decreases. And from this diagram, we see that
basically the maximum power occurs at the knee of this IV curve, which is also the peak of the power curve, the PV curve. And we want to, if we want to optimize the amount of power produced by the PV module, we have to have some sort of device that forces the PV module to work at this point, which is called the maximum power point, or the MPP point. So, so basically that's what my project will be about, to figure out how to track the maximum power point so that we can, so that's how we optimize a solar module. So this method is called maximum power point tracking, MPPT. And there are already a lot of methods for this. These four are the most common methods. There's also like a lot more methods, but so for this presentation, I will talk about fractional open circuit voltage method and the perturb and observe method. So okay, so this is supposed to be V subscript MPP, but yeah. So the fractional open circuit method is very simple. It's basically assuming that the maximum voltage, the maximum power point voltage, is equal to a constant K times the open circuit voltage. The open circuit voltage is basically just when you disconnect the PV cell from the load temporarily, so you can measure the open circuit voltage. So because the IV curve, I mean the PV curve is characteristic even for many like different irradiations and temperatures, by knowing the open circuit voltage, you can estimate what the maximum power point voltage is. So that's how this method works. That's how you can determine what the VMPP is. But so this method is like more easy to implement than most of the other methods, but okay, but there's some problems, which is that because you're using a ratio K to estimate it, it might not be that accurate. And also, every time the environment changes, you need to measure the open circuit voltage again. Every time you do that, as I said, to measure the open circuit voltage, you have to disconnect the PV module temporarily. So that can result in a loss of power. But one of the ways to get around that is that you can actually use a pilot PV cell. So this is the PV cell that has the same characteristics as the actual PV module that you're using. But you can just disconnect that to test what the open circuit voltage is without actually disconnecting your main PV module. So the other method is called perturb and observe. Basically, this method is also really simple. By perturbing the voltage that you're providing to the module, you can determine whether you have an increase or decrease in the power production. So say your point is here. If you increase the voltage and your power increases, then you know that your maximum power point is to the right of your current power point. But if you're on the other side, your maximum power point is going to be on the left side of your current power point. So you know where to shift your voltage, how much voltage you're providing. So that's how you basically can track the maximum power. So one of the problems with this method is that if your irradiance changes rapidly between the points where you are perturbing the voltage, then you can mess up this algorithm, because if the algorithm thinks that it should be moving right, but then the irradiance changes so that the maximum power point is now this point is to the left of that point. So if you actually moved here, then it's still going to think that it should go right, but now the actual point is to the left of to the left of where it once was. And so obviously when this happens, that the system is gonna get confused, and it's gonna slow down the speed that your algorithm can converge to the maximum power point. And the speed of convergence is one of the main criteria of maximum power point trackers. Okay, so I'm gonna be implementing this thing in Simulink using MATLAB. And so this is not what I made. This is just some YouTube tutorial. And but it's just to give an idea of what's happening. So you have any irradiance coming in, you have to model the PV cells, and then basically this is a simplified model just to show how things can change. And so the PV module is connected to a variable load, and then basically using probes you can figure out the IV curve and the power curve. And you will get, so these results that I expect with different irradiance, different temperatures. And so as you can see, as the irradiance changes, your maximum power point also changes a little bit. And yeah. So the Simulink model will consist of so the PV array, and then the DC buck converter, which so the PV array also has a control, and then a DC AC converter, which has another control, and then it's connected to the utility grid. So basically the idea is to sense the voltage and current, determine the maximum power point, and using the controls, we can adjust the duty cycle of the converters to adjust the maximum power to the load. And yeah, so that's my part.
Okay, thank you. Now you want Kim. You? The last one after that, Yao's back. With Yao. Is there anyone else that I didn't? Okay, good.
Okay, so my topic, project topic is distributed power system state estimation. What is state estimation in power system? I think in this semester we've all learned that it's very important to know the voltage magnitude and the voltage phase at each bus, because we need to control the operation of the power system. For example, if a generator wants to send a certain amount of power to the other bus, they need to know the voltage magnitude and voltage phase. So we call it the magnitude and phase at each bus as a system state in power system. And the task of the state estimation is to it's fine. Is to
use the mic.
Oh, okay.
Probably okay.
Okay. So the task is to estimate the magnitudes and phases at all buses with the measurements with the meter readings across the power grid. And typically, the standard measurement include like active and reactive power injection at buses and the power flows across the branches or across the connections.
Note that the recent technology of like PMU allow us to directly measure the phases and the magnitude of the buses. However, the cost of the installation and operation of those type of devices is very, very high, which prevent us from using it in large scale. So for this project, we basically focus on the problem with the classic measurement, type of measurement. And also to prevent, to avoid further complication of the problem and focus on the real issue of the distributed estimation, we adopted the DC approximation. And we also learned this in the class, that if we assume that the voltage magnitude is very close to 1 pu or 1 per unit, then we only have the for at each bus, we only have the voltage phase to be estimated, and the magnitude we simply just assume it's equal to 1 or approximated to 1. And also we assume the voltage angle difference is very small, so that we can employ the first order approximation for the sinusoid waveform. And the third assumption is the branches or the connections in the power grid is lossless. That means there's no reactance for the transmission lines. As such, then the reactance, reactive power is approximated as 0, and we have this, we arrive at this simple linear relation between the active power flows and also the power injections between the system state here. As remember that this is the phase of the voltage, and here Xij is the reactance between the bus I and J, and it's assumed to be known. If there's no connection between I and J, and this number is infinity, which means this value is equal to 0. Okay, so if we align all the measurement of reactive power in the vector y here, and align and put all the all these bus voltage phases in the vector theta here, we get a simple linear equation for this for our problem. Here the H is a lone matrix which relate the system state with the measurement, and it's determined by the measurements and the network topology. And N here is a noise vector accounting for example, measurement noise, or there will be some modeling uncertainty. And so if we want, okay, so this is just an example of the IEEE 14 bus system. This is another, it's more abstract graph for this system. We see that these circles are buses, and we see that the dot here, those dots means the sensors that measures the power flow between across the branches, and the squares here stands for the sensors that measures the power injection at each bus. And our task is to reverse or to estimate the theta from this power flow or power injection measurement. Okay, so if we look at this problem as globally, that means we simply need to we simply can obtain the estimate by solving a least square problem. And here we use the L2 norm. If you are familiar, it's just a vector inner product. And in fact, this cost function here, solving this, let's say this is a global cost function, and we obtain the estimate by minimizing this global estimate, global cost function. And in fact, we can obtain closed form expression for the estimate. However, although this looks similar, very straightforward, if you really think about this, H here in the real physical system is a very large matrix. And the inverse this matrix could be a huge task, could be computationally infeasible. So this has motivated us to look at this problem in a distributed fashion. Also, for this example, we want to, for example, we divided the whole network into 4 sub-areas. So for each sub-areas, we have smaller number of buses. And each area will estimate their local state vector based on their local measurements. Now, it's like we've divided the global problem into a sub-problem. But the problem is, let's say, okay, but still, let's setup, we mentioned the setup and the motivation. Okay, another reason is why we want to consider this problem is because it's due to the deregulation of the energy market. We know that now a large infrastructure now is actually operated independently by several or multiple IOS. And there are, let's say, one IOS, each of the areas might stand for IOS or a local utility. So that's the motivation of the problem. And still, our objective is to minimize the global cost function. And in a very, very ideal case, if these areas, there's no interconnection between these areas, then we arrived at, we have a 4 independent system. In that case, the H here, in fact, is a block diagonal matrix. That means this global cost function can be written as a sum of the local cost function. And then minimize this global function can be divided into sub-problems, which are solved in parallel independently by these areas. But in reality, unfortunately, that's not the truth. We have seen from these figures, we see that we have a lot of interconnection between these areas because they share the same infrastructure, that's why. So here is what a real H matrix looks like. We see we can see that it's very close to be a block diagonal, but it's not precisely the block diagonal. For example, here, these 2 areas actually share 2 buses because of the interconnection. Let's look at this group. The local vector is 1524. Let's take an example. The area 1, it's 152. But also, because of this interaction, the measurement here actually involves the other bus at the other area. So that has complicated our problem. So how to solve this problem so that we can divide the problem into sub-area problem? The first step is to, let's say, we duplicated we duplicate the shared buses and augment each local state vector by those shared buses. By doing that, if we keep the measurement here, vector here, unchanged, and by duplicating these 2 phases here, we see it's like we augment the state vector, and the matrix actually is stretched to a wider matrix. So then, by doing that, that means we actually are changing the matrix into a block diagonal matrix. For example, here, if we duplicate the theta 9 here, then these 2 matrices are pulled further, and there will be no overlap. So, okay, so if we do that, then the global cost function are written as a sum of the local estimation cost. And then we can further, the sub-areas can just solve their local problems independently. But there's a problem for that. One major problem is since we duplicate, we actually are creating more thetas than we need, or than the real world. So that by doing that, we are actually changing the global cost function. That will yield suboptimality for this problem.
Can you wrap it up in a minute?
Okay, sure. So then I came across this work where they deal with this problem in a very clever way, in my opinion. So they also basically did the same thing as I did before, augmented the local state vector. But they imposed one more constraint. The constraint, the intuition of this constraint basically means, okay, you have created new parameters, but you need to let the shared buses to be equal with each other, because they are actually in real world they are only the same buses. So by adding this constraint, again, this formulation will be exactly equivalent to the original problem we have. So that's why I think this is pretty clever. And they also, again, they further introduce some auxiliary variables so that the ADM method can be employed. So the idea of ADM is to fix one variable and update the other, and then do the other way around and iterate until the algorithm converge. Okay, so to wrap this, so the notion behind is to each sub-area solves their local problems. However, they want to they use the message passing to consent or to agree upon the shared buses the face value. Okay, so that's the notion behind. And these are some relevant references. So if you are interested, I'd be happy to discuss about them. Okay.
Okay, thank you. And you're after this. You're the last. You need to pass the one.
Oh, yeah.
Not reading your memory?
I don't think it's recognizing it. Can I just use my laptop then?
Yeah.
Okay.
Do you have the HDMI or you need mine?
No, can I borrow one if you don't mind?
Make it full screen, probably get the right size.
How do I do that? Sorry.
You go to view, for example. If you can go to view, no, takes time this way. Do you have a video or something?
No.
No, it's slow. Okay, good. Click on it. Oh, okay, you see it. Okay.
Is this?
You might need to mirror this. That's the challenge.
Should I just talk without this?
No, that's fine. Should we try again? Yeah, it's a little slow processing.
Well, why is this not recognizing the hard drive? I don't know why. But whatever, it's connected. Okay.
Okay, go to system preferences.
My computer is like really slow, so.
You're almost dead too.
Okay, should I let the other person go
Yeah, that's
first?
what you can just switch. Are you ready? Who was the last person? You're the last. You try now.
Yeah, take this out. Oh, it's here.
Wait a minute. This one, right?
Yeah. Use the mic, please.
Oh. So I'm going to talk about the concentrating solar power in a sustainable future grid. And I know today lots of us have talking about solar powers, but still I want to give a general definition of it. It's a conversion of sunlight into electricity, but there are two ways to use the power. One is directly using it, which we have talked about earlier by other presenters. It's based on a photovoltaic effect. It's a way of directly use the sun solar radiation and to put it into use of electricity. And another one is the indirectly usage, which is what we are going to talk about concentrated solar power. So this is using lenses or mirrors and tracking system to focus the large areas of sunlight into small beam. So such a technology, it uses the direct solar radiation and to transform it into a huge amount of heat. And then you put it into the turbine to drive the turbine and then turn into the electricity grid. So about the PV power system, well, I will just talk it quickly. It's a small to medium-sized applications, and it can feed low carbon energy into grid. So this is a small residential application of PV system, which is they use modules to receive the solar radiation and put it into the inverters to trans the direct current into the alternating current. And there's also still a large scale PV station, which is called PV power station, also known as the solar park. This is for the commercial, for utility level usage. So now I'm going to talk about the concentrating solar power. So CSP system capture the direct beam component of solar irradiation. So they're not able to use radiation that has been diffused by clouds or dust or other factors. So this makes them best suited to areas with high percentage of clear sky days in locations that do not have smoke or dust. So there are mainly about 4 types of configurations, and each technology boosts particular advantages and in some cases particular market segments. And project and technology developers are actively pursuing all types of CSP technologies. So the first one is parabolic trough. So parabolic trough is a shaped mirrors produce a linear focus on the receiver tube along the parabolar's focal line, as illustrated in this picture. So the complete assembly of mirrors plus receiver is mounted on a frame that tracks the daily movement of the sun on one axis. Relative seasonal movement of the sun in the other axis result in lateral movement of the line focus, which remains on the receiver but can have some spill at the raw end. So trough systems using thermal energy collection by evacuated tube receivers are currently the most widely deployed CSP technology. In this configuration, an oil heat transfer fluid is usually used to collect the heat from the receiver tubes and transported to a central power block. And the next is central receiver tower. A central receiver tower system involves an array of heliostats, which is large mirrors with two-axis tracking, and that concentrate the sunlight onto a fixed receiver mounted on the top of a tower. This allows sophisticated high-efficiency energy conversion at a single large receiver point. Higher conversion ratios are achieved compared to linear focusing system, and this allows thermal receivers to operate at high temperatures with reduced losses. And the third type is linear Fresnel reflectors. So linear Fresnel reflector system produce a linear focus on the download-facing fixed receiver mounted on a series of small towers. Long rows of flat or slightly curved mirrors move independently on one axis to reflect the sun's rays onto the stationary receiver. For the thermal systems, the fixed receiver not only avoid the need for rotary joints, but can also help to reduce convection loss from a thermal receiver because it has a permanently down-facing cavity. And the last one I want to mention is the parabolic dishes. So dish systems like troughs exploit geometric properties of parabola. The reflected direct beam radiation is concentrated to a point focus receiver, and its operating temperature can be over 1000 Celsius, similar to the tower systems. And dish systems offer the highest potential solar conversion efficiency of all the CSP technologies because they always present their full aperture directly towards the sun and avoid the cosine loss effect that the other approaches experience. They are, however, the least commercial mature as the technology is still developing. So I want to explore more about the technical attributes of CSP and what I see the potential in this technology. So for stable and reliable electricity grid operation, availability, firm capacity, and load flexibility are very important. So in the past, these features were achieved by consuming ideally stored primary energy sources such as fuel, oil, natural gas, or coal, and by burning them on demand in order to deliver electricity at any capacity needed and whenever required. Using freely flow energy from renewable sources, which is not as easily stored as fossil fuels, will change this picture in the near-term future. While the share of variable fluctuating renewable sources is going to increase, flexible fossil and renewable energy sources will gain increasing importance and value. So about the flexibility of the power technologies, this refers to the minimum capacity at which a plant can be operated before it has to be shut down completely. The range of power capacity that can be freely set by the plant operators without limitation, and the possible maximum speed of capacity changes that can be achieved. So once shut down, the time required for restart is also relevant as it limits the availability of the plant. Especially thermal power plants take a long time to return to the grid if they are not kept on standby status, which however implies the consumption of fuel or other stored energy without generating electricity. So flexible power will be an important element of transformation of the electricity sector toward higher shares of renewable energy. It will be required to compensate fluctuations of supply from sources such as wind and PV systems that strongly depend on the changing availability of the natural resources. So another important attribute of power supply is firm capacity. As an example, baseload power plants such as nuclear plants are not necessarily very flexible, but most of their nominal installed capacity can be considered as fully to be put into utility. PV and wind power do not have the quality of firm capacity because a simple cloud or calm can reduce the available capacity to a few percentage to zero. Wind and PV systems are flexible because their capacity can be reduced, but only when they are running. However, in contrast, CSP plants can produce flexible power on demand and can rely on their thermal energy storage capacity and eventual backup fuel to provide firm and capacity whenever required, which is not the attributes of other renewable energy. So it's very crucial about this firm capacity. So talking about reactive power, there is increasing concern about the availability of reactive power in future electricity grid. That is, to a great extent, would be fed by renewable energy. As the power generator of a CSP plant is the same as the one in conventional steam cycle power station, the provision of reactive power is nominal service function that any CSP plant can deliver for stable grid operation. And then the most important part of CSP is its competitive cost. So when we evaluate high technology, whether we can put it into the utility is whether it can be commercialized. So cost is very important for the for the commercialization of technology. So here's the figure. Sure. So here's the figure shows the cost in the future, predicting the future trend, which expected cost of CSP versus fossil fuel-powered electricity generation under the assumption that a learning rate of 12% rate can be applied to CSP expanding on a global scale. So we can see from the figure that CSP already has competitive with electricity from fuel oil and could break even with natural gas around 2020 here. So it's around it. It's two lines predicting its price. So again, when comparing these options, one must consider that technical quality of CSP is almost equivalent to that of fossil fuels, whilst economic equality with respect to cost stability is considered higher. And another is also, so today there's still no incentive for electricity producers to guarantee stable electricity prices for a long period. This type of quality is not a request yet because fuels have been cheap in the past. However, this picture changed dramatically, surprising all national economists worldwide with up to 450% fuel cost escalation within the past 10 years. So the consequences of not requesting price stability as an intrinsic quality of energy supply structures and instead insisting on short-term least cost solutions. So I think CSP will have great potential in the future sustainable electricity mix, as it has the characteristic of flexibility and firmability. So it can deliver power on demand at any time without the fluctuation of the weathers. And also this technical quality, to this technical quality, it has the economic advantages and very competitive from power from fuel oil. And also it has lots of environmental benefits, but because solar is carbon free. So, well, that is my idea about the CSP.
You don't need a computer? You good?
No, I have.
Oh, you got it. And
so I'll try to make mine as short as possible because it overlaps a lot with the previous presentation. So my presentation is like analysis of technology innovations for expansion of solar energy market, and it's at the global level. And I'll be talking about the solar energy market and then just like what are available at the market currently, the solar PV versus CSP, and then some of the challenges and the areas of research, and then I'll talk about the conclusion. So as you can see in this graph, like solar market
expanded really rapidly since 2010, and that's mainly due to the price reduction of the solar PV, which people explained. And actually, currently, the solar energy is 0.3% of the whole electricity generation. And even in Germany, it's like 5% of energy is generated from solar, and in Italy, it's like 7%. So it's a big proportion. And so there are two major methods of generation. One is PV, and then one is CSP. And then PV is around like 86% of the whole solar power generation, and that's because of the price. And CSP, although it has a really good storage ability, the only reason it's 16% of the whole market is because of the price that it is, and then it's much less efficient than PV. And yeah, and then PV converts the energy directly from sunlight to electricity, whereas CSP converts the energy, the solar into thermal, and then turns into electricity. So while PV can be both off-grid and on-grid, connected to the grid, the CSP, because it has to be a large scale, it can only be connected to the grid. And some of the technology associated with PV is like solar array, solar tracker, solar inverter, battery emitter, whereas concentrated solar power, like, oh, I'm missing something. Oops. Okay, whatever. Anyways, those are the, wait. Yeah, those are the technologies associated with like the two different technology. And I'll be focusing on the solar inverter and battery. That's like the main issue for the PV. And I feel like I'm missing something here, but anyways, yeah, because like for PV, although it has a really good efficiency rate, because we cannot store the energy, that's like the major problem. And also we have to, for the solar PV, we have to convert the DC power into AC power, and that inversion efficiency also affects the efficiency of the PV. Yeah, so for CSP, the major areas to improve is the cost reduction, because it has to use like a really high temperature in order to create thermal energy. It costs a lot. And we also need to research on the efficient rotation, because it needs a lot of sun rays compared to PV, so it has to like actually maximize the amount of sun it gets from the air. But the benefit of the CSP is that it can store energy, whereas the solar PV cannot, because it turns into thermal so that it can store energy in some form of liquid, whereas like solar PV just evaporates or it just disappears. So for my suggestions for the market expansion is that we really need to standardize the regulations, like how to benefit the customers and how to like price the energy. And I feel like there are a lot of like rooftop solar PV where you can put on the roof, but I feel like for the market expansion and more standardization, I think on-grid power systems of utility scale is necessary for solar power. And because CSP has the advantage of storage compared to solar PV, combination of those two technologies can be complementary to each other. And that's my project. Thank you.
Okay, we're done with the course, so you can pick up your homework. Grade the homework 4 and 5 or 6. Come here.
Great. This is yours.
Actually, no, I borrowed from someone.
Oh, it's someone else.
You want me?
May 14th. I just need just one day. Yeah, that's good was the case. Today, that's not a problem.
Yeah,
Well,
thank you. If you could, what the
But the whole lot of I don't think it's exactly. It's up to you. I don't, if I want to create a product, I'm not consider how many other people are working on it.
Let's decide how much material you need based on the topic. How to predict the keyboard for automation. It tells you how to predict the behavior based on the Yeah, you should email us. Make sure that I never saw it. If you look at my website, there's a teaching part of sample project. There's a lot of variability. The topic. The words.
The bloodshot is fading away or still there?
It's not like graded based on the topic. It's not graded based on the topic. Your job.
Conosce André, lì, conosci il livello 4 André, perché ne entregò atrasato. Vai, che dice, entregò atrasato, ne c'era più, sei là, negativo.
Most of the time, leaving, just make sure that you just collect. Yeah. So it's 10% per day. Okay. The key thing we do is always student might email you and try to get on that.
Did you find your book? Yeah, I found it. Thanks.
You're done?
You did a good job. So, like, one of the homeworks, I forgot to, like, I think it was homework 3, I forgot to hand it in, but I emailed the marker, and he never replied, and I didn't see it in the...
Okay. What's your name?
You and Chen.
You need to, okay, send me an email and tell me the